Okay, so this is a question from the 2012 paper 3, question 7b. So part 1 state the relation between E field strength E and potential V. Now this is a giveaway, okay? So E is just equals to negative dV dr. Okay, we'll always need to know the interrelationship between the different formulas. So this is a question that proves that. Okay, so next part, two spheres are given, A and B, diameters. Okay, take note it's diameter, so the radius is half of it. Okay, so radius is 9 cm, and that's why I see 9 cm here, and the other radius 6 cm. Okay, so this part of the graph is going to be 6 cm. So for the centers of the sphere are separated by 50 cm. Okay, this is here. Point P has a distance x away from the center. Okay, and the variation of x of the electric potential V at P is shown. Okay, so that is on the graph on the right side. State and explain the direction of the E field at point P where x equals to 25 cm. So x equals 25 cm is this part, okay? And we can see that the potential is positive. So what this means is that we are going to get positive charges here, positive charges here. So there will definitely be a neutral point, and the neutral point is always nearer to the smaller charge. But now let's see, we do not know which charge is smaller. We only know that the potential is smaller. But what we can see from the graph here is that the neutral point should be at 35 cm. Why? Because E equals to negative dV dr. So neutral point is where E field is 0, dV dr is 0, it will be at the turning point. So being at 25 cm is before the neutral point. So the neutral point is somewhere here. So this is like the neutral point. And we know that because of that, the direction of E field or the force of the positive dash charge will be here towards the right until 0, then after that towards the left. Okay, so we only need to explain at point P when it is 25 cm. So the state is pretty straightforward. The state is going to be just the force, the direction of E field. Okay, remember it's the direction of force of the positive dash charge of the electric field. Okay, let me just drag this out. Okay, the direction of force on the electric field is towards the or towards sphere B or towards the right. Both are okay. Okay, so explain. Okay, the neutral point, which is the turning point, is at x equals 35 cm, which is the turning point of the graph. Maybe we can add of the graph. So 35 cm. At 25 cm, the E field due to A will be stronger than B. Hence, the E field is rightwards. Okay, due to A, it will be stronger because neutral point, then they are the same. Okay, so this is pretty straightforward. Okay, now next part. Use the figure to determine the force on an electron placed at point P where x equals 35 cm. Okay, so at the you can see at the turning point. Okay, at the turning point, the E field is 0, so the force should be 0. That is pretty straightforward. Okay, so why 2 marks? Not sure. Probably we can just use x dv dx or r. Let me see. Oh, okay, we just use. Oh, they use x. Okay, so probably I could use. Let's see. Mm, okay. By the way, I will need to add on that for this E equals to negative dv dr. Okay, for this case is that we are using x instead of r. Okay, you see horizontal axis is x. So one more thing is that to state, okay, basically best to use a statement. Okay, use sentences. So let me just put a sentence here, okay, as to be a more proper answer. The electric field E is the negative of the potential uh, of the negative of the gradient negative of the gradient of the potential distance graph. Maybe I should put in electric potential distance graph, okay, to be more proper. Okay, so that is for this one. Okay, back to this. So determine the force at point P now. For point P, again, neutral point. So basically, we can say that this one we need to explain a little bit. From the graph, it is there's a turning point. Basically, it's a repeat of the earlier parts. Okay, they repeat the same thing again and again. So there's a turning point at x equals 35.0 cm. Since E equals negative dv dx, E field is 0. Hence, force on electron it equals 0 Newton. Okay, that's all. So for this one, the working is just really just explanation. Okay, that's the working already. Next, by making references to the E fields, explain why potential is constant between x equals to 0 and x equals to 9 cm. Okay, so this is the same as the earlier the 2014 question. Okay, so we need to explain again that E field is 0 because you need to make reference. So E field is 0, that's why potential is constant. Okay, because E equals to negative dv dx. Okay, so again we just need to explain. Let me just zoom in a little bit. Okay, so the free charges, okay, the electrons in the conductors, in the spheres. Let me just shift a little bit. Electrons in the conductors reside on the surface and are not moving and are not moving. Hence, there is no force and electric field is 0 within the actually maybe yeah within the conductors within sphere A. Okay, because they are only specifically asking between 0 and 9. Since E equals negative dv dx, which is and it's equals to 0, B, the potential V must be constant. Okay. A student states that the potential decreases with x for distances for 10 to 25 cm according to this. Without using a graph, use data to show whether the student is correct. Now, this particular question came up a few times in the past. So may not be this chapter, okay, it can be a few chapters. So basically what you need to do is to take a few values and show whether it's constant or not. Of course, if it's constant, you probably will need a few more values. But for this question, it will not be a constant. Okay, that's why you'll need to explain it later. So you'll do it at least 3 sets of data because it's 3 marks. Okay, based on number of marks. If Kiasu can do 4, okay, that's basically if you are doing, let's say they are actually a constant. Okay, so they want 10 to 25 cm. Okay, so that is this the graph is here. Oops, it's moving. Okay, let me just shift a little bit. So at 10 cm, okay, let me just change the color a little bit. 10 cm to 25 is here. Okay, so you can take 10, 25, these are the endpoints you must take. Okay, you want, you can take 15, 20, then easy. Then you read off at 10. At 10, you can read off 750. Okay, volts. At 15, you can read off 500 and around 515. Okay, around 515. Maybe a bit higher, 516, 517. Okay, but we read off to half a square. At 20, you can read off at 405. And at 25, you can read off maybe 340. Okay. So you want to check V as a constant, you'll do something like this. So at V X, okay, you draw a table to show, and then you multiply what is Vx. Okay. So V, okay, we have X equals to 10 cm, 15, 20, and 25. And we have our first one at 750, 515, 405, and 340. Okay. So what you need to do is to multiply and show if they are the same or not. Okay, then you'll see whether they are constants or not. So 750, okay, times 10 divided by 100, basically just 75. 515 times 15 over 100, you'll get 77.25. 405 times 20 over 100, you'll get 81. And 340 times 25 over 100, you'll get 85. Okay, although there are still small differences, but you can see that it is still, I mean, in the readings of the graph, we are rounding it off, but the Vx is pretty huge in terms of the differences. Okay, so therefore, Vx is not a constant. Okay, so just write it's not constant. Student is wrong. Okay, that's our conclusion. Suggest an explanation. Okay, this is pretty simple. Vx is a constant of V is equals to KQ over X only for point charges. And not just point charges, but single point charge. Okay, so that will be our explanation here. Vx equals constant only applies when it is a single charge. But this question is two charges, okay? It's affected by two charges. Only applies when there is a single point charge. However, figure 7.2 shows the graph of the potential graph due to two different charges. Okay, show the potential graph due to two different charges. Okay, we got two charges. Okay, in this case, there are two charges, sphere A and sphere B acting in between. Okay, so that's why it is not constant. It's not inversely proportional. Okay, so this equation is not valid. Okay, next part. Electron initially at rest approaches the spheres and passes through between the two spheres. Calculate the minimum speed as it crosses the line joining the centers of the two spheres. So this is just a simple conservation of energy question. So there will be a loss in EPE equals to gain in KE. Why? Because it starts from rest. So definitely KE gain. Okay. So at the same time, we can see that the loss in EPE, we need to look at here. Okay. The minimum speed will be by the minimum gain in K, and the minimum gain loss in EP, which will come from the minimum potential here. So at x equals to 35, you can see that here the value is going to be 295. Okay, so that is the very minimum value. Okay, so loss in EPE, loss is initial minus final. Okay, so 0 is the initial, is at infinity, minus, okay, because it's an electron, so we know that it's going to be the energy W work done is actually QV, so we can actually apply this here. Q is negative 1.6 times 10 power minus 19, and V is 295. Okay, so that is the loss in EP, which is the gain in Ke, half times mass of electron, which is 9.11 times 10 power minus 31, V square minus 0 square. Okay, so this is the gain in Ke. So from here, you can actually calculate the V. Okay, 1.6 times 10 power minus 19 times 295 divided by 9.11 times 10 power minus 31. Okay, divide by half, then square root. You'll get your speed as 1, 2, 3, 4, 5, 6, 7. 1.02 times 10 to the power of 7 meters per second. Okay, so let me just write down here. Now, last part. Describe the path of the electron for the minimum speed here. 2 marks. So, for this question, okay, I will bring in this diagram that I have here to try to explain. So, the path of the electron, right? Okay, now what happens is that, okay, for this diagram, for this case, the two charges are of the same magnitude. Okay, but what happens here is that the question is they are of both different magnitudes. So what happens here is that we will need the electron from infinity to come towards here, pass through the center. It must pass through the minimum V, which is 295 volts, okay, before it goes out. Now, why this is so is because you can see that the different values of V means there's different values of gain and energy. So there is a there is a there there is a more energy if it's like other parts, okay? And at 35 cm, the gain in EP will be the least, so the gain in K will be the least, okay? So what happens here is that the electron will definitely pass through X equals to 35 cm, and okay, and I believe that for 2 marks, you'll probably need to say that, okay, it does not move here, okay, so you can describe any path as long as it does not move through like here, because here is different already. It's, okay, the potential here will probably get very large. Okay, the potential here also will get very large. So it's hard to explain when it's like going through these two directions. It's actually easier to go through here. So I will say that we can actually say that it will cut through here perpendicularly. May not be perpendicular, but it will definitely not be an angle. Okay. So the path of this electron for the minimum speed, okay, it will be a path. The electron will move in a path. Okay, let me just expand this again. Electron will probably, you can say many paths, so there are actually infinite number of potential answers, but of course there are a few wrong answers. Okay, so move in a path. The electron moves, describe the path. Okay, maybe it's like one of the path. The electron moves in a path that is perpendicular to the line joining the two spheres. It may not be perpendicular, but it's definitely not parallel. Okay, so I think it's easier to write that. Okay, and cuts through the point where x equals 35 cm. Okay, so that should be the answer for this question.